just going to look at some applications of our number patterns. Right, so here's one that comes from the HSC. It was doing at HSC, admittedly, and here we go, Heather, who's going to swim every day to improve her fitness level. Now, I don't know if any of you do swimming for fitness, by the way, but if you're not used to swimming laps, I would recommend that day one you don't swim 750 metres. You'll be lucky if you can do 50 on your first day. It actually is quite hard. But anyway, here's the question. On her first day, she's going to swim 750, and then each day after that, add an extra 100 metres on. Very ambitious. So in other words, she'll swim 850 on the second day, 950 on the third, and so on. So they're spelling everything out in the HSC. The first question that they've asked is, write down a formula for the distance she swims on the nth day. So we need to extract the information. So we read through it and go, oh, look, first day, 750. So A will be 750. And then we go, oh, every day we're adding on 100 metres. So D will be 100. So we know we have to find the nth term. So term n, A plus n minus 1D. Summing it in, so term n is 650 plus 100n. How far does she swim on the 10th day? 1 mark. Find a particular term. Term 10 we're going to find. So there's our formula we just worked out. Substitute in. So on the 10th day, boy oh boy, you're going to swim 1,650 metres. Okay. Total distance she swims in the first 10 days. So this now becomes sum to 10. So we're going to find sum to 10. N over 2, 2a plus n minus 1d. Sub it in. There we go. 12,000. I could have used n a plus l. Amazingly, comes up with the same answer. So in 10 days, a total of 12,000 metres. Now, as you do, I mean, look, this is a practical question, of course. So one of the things we would be curious of is, well, look, how many days does the total distance equal the width of the English Channel? That's a logical question to ask, really, when you think about it. By the way, that's a distance of 34 kilometres. So we want to know when the sum to n is equal to 34 kilometres. So 34,000. A is still 1,500, D is still 100. Subbing in. And, oh, we get a quadratic. Fortunately, everything divides by 100. That makes life a bit easier. Multiplies together to give minus 680. Adds together to give 14. There we go. Two possibilities. But of course, we're answering a practical question here, and only one of these makes logical sense. So which one would be the logical answer? Minus 34, that's right. Because, because that means that we managed to do that 34 days ago, and so we don't have to do it now. We can stop swimming. No, it took 20 days to swim 34 kilometres. Let's have a look at another question. Sales are declining 6% every year. Not a very good business. So they've got 50,000 items sold in 2001. Which year will sales first fall below 20,000? So we've got a GP this time. A, 50,000. Ratio, but we've got to be careful here, is declining by 6%. So the ratio is not 6%. The ratio is actually 94%. So 0.94. We want to know when is our general term below 20,000. Okay, AR to the n minus 1, subbing in. So really, it's just the same sorts of questions that we were seeing before. We're trying to put a practical spin on it. All right, log both sides. We're going to divide by the log of 0.94, but of course, log of 0.94 is negative. If you change the sign. Thank you very much. Okay, so n minus 1 is greater than 14.8. So n is greater than 15.8. They say during which year? So it's the 16th year or 2016 or whichever will be the first time. Let's look at another HSC one. 2005. Anne and Kay. employed by an accounting firm. Conditions of employment. Anne has an initial salary of $50,000, and each of the following years she's guaranteed a salary increase of $2,500. So they're the conditions she agreed to. Kay also starts on $50,000. She agreed on different conditions. Each of her one's going to increase by just 4% each year. So let's have a look at Anne. Anne is arithmetic, of course, because we're adding. Her A is 50,000, common difference, 2,500. Whereas K is geometric. Also starts at 50,000, ratio, not 4%, but 104%, because we're increasing by 4. Okay, part 1, 2 marks for this. What is Anne's salary in her 13th year? So we want to find term 13. So A plus N minus 1D, subbing in, there's her salary in the 13th year. It's now $80,000. What about K? Who got the better deal? So now it's a geometric series. So AR to the N minus 1, so 50,000, 1.04 to the power of 12, $80,051.61. K slightly, but she has got the better deal. So by what amount does the total amount paid, so over all the years, in her first 20 years, so clearly now K will continue to get better and better and better as the years go on, but over the whole of the first 20 years, how much more money is she going to get than Anne's going to get? So all right, we're finding sum to 20. So for Anne, N over 2, 2A plus N minus 1D, Anne's earned $1,475,000. K, hers is geometric, and she's earned $1,488,903. So the difference, obviously, we subtract one from the other. There we go, an extra, well, almost $14,000 there. Find the limiting sum of the geometric series. Here's a nice, easy one. If they give us a question like that, we say, thank you very much. Remember, sum to infinity, A on 1 minus R. So A is 3/4. The ratio is 1/4. Subbing it in, 1. Oh, 2 marks. How generous. Okay. Here's a question, also on limiting sum, but you notice the first one was question 1. This one appeared in a question 7. Reason being, a little bit harder, you would think. It's still fun, the limiting sum. Question's exactly the same, but look what they did. Surds. Ooh. A is 2. The ratio is 1 on root 2 plus 1. So A on 1 minus R. Ooh, messy. There we go. Let's play around with it. And eventually we get 2 plus root 2. Remember I was saying sometimes they're more interested in whether you know the condition, not necessarily the answer. Explain why this geometric series does not have a limiting sum. Well, we know the ratio must be between minus 1 and 1. So the ratio of this is 1 on root 2 minus 1, which if you punch that into your calculator is around about 2.4. So it's bigger than 1. So that's what they're looking for, that you understand what the condition is for a limiting sum. And now, a humdinger, question 9A. 2004, this was back in the days when they just had 10 questions. So this is right near the end of the paper. So 1 minus tan squared plus tan to the power of 4. So A is 1. The ratio is negative tan squared. First part of the question is find the limiting sum. Notice they say when it exists, because it is possible for tan squared theta to be bigger than 1. So we say, well, when tan squared theta is less than 1, that's what this is basically saying, formula exists. So all right, A on 1 minus R, we get 1 on 1 plus tan squared. That's probably where a mere mortal would stop. But we'd go, no, no, no. 1 plus tan squared is, of course, sec squared, and 1 on sec squared is cos squared. So there's our sum to infinity, cos squared theta. Part 2. We know that one branch of a tan curve is minus pi on 2 to pi on 2. They're the asymptotes on the tan curve. So they're actually asking us for which values will tan theta be between minus 1 and 1. We know that the limiting sum is in between minus 1 and 1. So we're saying when is minus tan squared theta in between minus 1 and 1? So when is, divide everything by minus 1, but of course if you change the sign, you change the sign. So now it's 1 is greater than tan squared theta is greater, but that looks ugly. Oh look, we're back where we started from. Except now it's tan squared theta is in between minus 1 and 1. So if tan squared theta is in between minus 1 and 1, that means tan theta is in between minus 1 and 1. So plus or minus pi and 4. Right? Tan is 1 at 45 degrees or pi and 4. Just to give a little picture. But if you see the graph here, we know that tan of pi on 4 is 1 and minus 1. There we go. So it's in between those two x values, which we know to be pi and 4 and minus pi and 4. We end up with a y value that's in between minus 1 and 1. So by looking at the graph, I can see theta must go in between minus pi and 4 and pi and 4. So it's only at those. So 7a, this is actually in the Year 12 book, by the way. But those who are looking at their schedule religiously, such as someone here was, would know that it was book 2 we were working from today.